Alright, so welcome to this video on engineering dynamics, and in this video we'll be doing another sample problem for the kinetics of a point mass, and we're still in the method of force and acceleration method. Okay, so for sample problem number 2, this is taken from the book of Hibeler. So it's engineering mechanics dynamics, Hibeler 12th edition. So it's a sample problem actually. Alright, so I think it's better if we'll just read it here from the textbook. So the sample problem says that a 10 kilogram projectile is fired vertically upward from the ground with an initial velocity of 50 meters per second. So the illustration is this. So it's something like a cannonball that's fired vertically upward. So I don't know why it's why you should fire a cannonball that's really vertically upward. Anyway, this is just a sample problem. So determine the maximum height to which it will travel if. So for case A, atmospheric resistance is neglected. So what will be the maximum height here? So assuming there's no drag force included, what will be the maximum height? And then for the case B, atmospheric resistance is measured as drag force as 0.01 v squared. So the drag force is directly proportional to the square root of velocity. So the drag force is Newton, where velocity is the speed of the projectile at any instant measured in meters per second. Alright. So here it is. So let's try to solve, for now, case A. Alright, so solution for case A. Okay, so first step is I usually try to convert these statements into figures or pictures. So we have this cannonballs here, or a cannon. So let's say this is the initial point. And so I'll use this file. So this is initial point. So it tries to fire up a object here. Okay, so we'll try to analyze this situation. So once you fire up something, the velocity here, as it goes up, the velocity decreases and decreases until it gets to 0. So once it gets to 0, then that's the maximum height it will reach, and then it will start to go down. Okay, so let's assume this is the maximum position. So that's the point 2 that we are trying to find. Okay, so let's try let's try to write down the initial conditions. Okay, so the projectile is fired vertically upward from the ground with an initial velocity of 50 meters per second. So we have this velocity here. V1 is equal to 50 meters per second. And of course, if that's the initial point, then T1 would be 0, and if that's the reference point, then the S1 would be 0. Okay, meters. So assuming that we have this positive direction. Okay, so here it says that this will be the maximum, right? So S will be x S max, but then the velocity here would be, since it's the maximum position, the velocity would be 0 meters per second. And then the value of time is, we don't know yet, right? So let's draw the free body diagram, FBD of the projectile. Okay, so it says the atmospheric resistance is neglected, so meaning that this is our object here. So the forces that's acting is just, the weight. So weight is equal to mg. If we'll try to solve it now, 10 times 9.81, so which is 98.1 newtons. So that's our weight. So for case A, we don't have to consider the resistance. Now if we also try to draw the mass acceleration diagram, okay, let's try to include diagram. So this is it. The direction is just like this. So MA, yes, MA. Okay, so let's say this is a y direction. Actually, it doesn't matter if whatever symbol you want to use, but it's just a one dimension, or it's just a straight line motion. Alright, so now we have this free body diagram. So the force that acts is just the weight. So now we can writing down the equations. Writing now the governing equation. So sorry, it's very unprofessional here, but of course this is the beginner kit for Arduino. This is what I use to support my lamp stand. All right, so I think that's it. I think it's fine. So writing now the governing equations. Let's try to move this one here. All right, so what do we get? We have summation of forces on the y direction is equal to mass times the acceleration in the y direction. Right, so we have force here. We just have weight is equal to mass times the acceleration, y. So weight over mass equal to acceleration. So it's actually it's the gravitational acceleration, 9.81 meter per second squared. So now that we have this one, we have to find this S max. So still it's a constant acceleration thing here, and then we have to find the kinematic parameters relating, acceleration, velocity, and then the position. So this is just the same as last time, and then the working equation for this that fits is this one, 2a. Okay, this is the ay, delta s is equal to delta v squared, right? So let's try to write it down. 2 times, what's the acceleration? It's actually the acceleration of this object is decreasing, so it's a negative acceleration. So negative a y, what's delta s? So s max minus s sub 1, which is just 0, is equal to delta v squared. Okay, so v sub 2, v at point 2 is 0. So 0 squared minus the initial velocity, which is 50 squared. So let's try to simplify things out. We have negative on the left hand side and then negative on the right hand side, so it cancels out. So let's write down the values. 2 times 9.81 times S max is equal to 50 squared. So S max is equal to S max is equal to 50 squared divided by 2 times 9.81. So we have 127.4 meters. All right. So it's just actually almost the same as the one we've learned in the kinematics. So it's just the same. All right, so let's try to solve another solution for case B. Okay, so for case B, now we will have a different free body diagram, but the scenario is still the same. We still have these initial conditions here and then the conditions at the end. So let's draw, drawing the free body diagram. Right, so we have here the object, we have the weight. Alright, so we have the weight here. Take note the motion is upward, so the weight is acting downward, and also since it's traveling upward here, the motion, so the drag force will be opposite to this, which is also downward, and the value for drag force is 0.01 v squared. Okay, so it's directly proportional to the square root of velocity. Alright, so let's set up the equation. Alright, setting up the equation. Okay, so summation of forces on the y direction is equal to m times acceleration in the y direction. Alright, so the forces we have, since we assume a positive in the upward direction, right, so this would be negative, So minus d minus w is equal to m times ay. Alright, maybe we'll try to express this ay in terms of position. Alright, so d squared s over dt squared. Alright, so this is the acceleration. And let's write down the equations. So minus 0.01 v squared minus, what's the weight? So the weight is just a constant, 98.1 is equal to, what's the value of m? It's 10 kg. So 10 times d squared s over, oh sorry, I think we have to write this one in terms of velocity first, because we have a velocity here, so I think it's better to, right, so not that one, we have to change that to m dv over dt. Right, so I'll cross this out. So it's equal to m dv over dt. Okay, so oh no, wait, I think not this one, maybe. All right, let's let me put that in another paper. So setting up the equation. Okay, so let's not put it this way. I think what will work best is this one, v dv over ds. So this equation would, I think this one is the best thing to use, since we have the initial and final values for the velocity, and then we have the initial position, which is just 0. So if we'll use this, then actually we can solve for the final position. Okay, so let me write it again. Negative 0.01 v squared minus 9.81 is equal to m. It's just actually 10. Right, so let's write 10 now. 10 times v dv all over ds. Okay, so let's try to figure out what kind of differential equation this is. So this is a first order, right? First order, and the first thing, if you encounter differential equation, is to check whether it's a separable equation. Because if it is, then it's easier to solve. So actually, yes, this is a separable equation. You can separate the s from the v. So here we have the v here on the left hand side. We have v, which is a constant, but we can take this together. Then you can see it's just a v and then the ds. So I think we can separate, right? Separating the variables, let's write this way. ds equal to 10 v dv all over negative, okay, let's factor out the negative here. So minus 0.01 v squared plus 9.81. Okay, so that's the equation now that we have. So what's this? So let u is equal to the numerator 0.01 v squared plus 9.81, and then if we try to take the derivative, so 0.01 times 2v dv, right? Okay, so 0.01 times 2, right? So okay, 0.02, 0.2 v dv. Now if we'll just isolate the dv on the right hand side, then what we get is d all over 0. I think the v dv here, so 0.02. Okay, so this is what we're going to substitute, this one and then this one for the dv. So the dv will be here, and then this one here on the denominator. Okay, so let's substitute. So ds is equal to 10, what's v dv? 10 times du all over 0.02, and then what's the, okay, take note this is negative. What's the denominator? That is just u. So let us simplify this. Negative 10 divided by 0.02, so it's 500. So negative 500. What's the derivative of this? Oh no, not derivative, I mean the integral. So let's try to integrate for now. Right, so the limit is, let's look at the limit. So from the first point is S0, then the final point is the S max. Now from here, this is a velocity term. So the velocity initial is 50 to 0. Okay, so what's this? The integral of du all over u. That's the natural log ln of u evaluated from 50 to 0. So here was the integral of ds. It's just s from 0 to s max. Okay, so here we have a variable here, a u variable, but we have to bring it back to the original variables in terms of v. So negative 500 times ln of, that's the 0.01 v squared plus 9.81, right? So evaluated from 50 to 0. All right, so let's apply the upper limit now. So negative 500. So if we substitute 0 into this v value, what we're left of is just the 9.81. So ln 9.81 minus, let's evaluate this term with v is equal to 50. So let's try. So 50 squared times 0.01 plus 9.81, so 34.81 minus ln 34.81. Right, so let's do some more math. So we have this difference, and then if you remember the properties for this is just this one, 9.81 divided by 34.81. Right, and then this one, what's left is just the x max. Okay, so let's try to solve this one. 9.81 divided by 34.81. So ln, the answer, times negative 500. Alright, so, nope, something's wrong, I think. I think something is wrong here. It couldn't be a 633 meters. Okay, so let's try to find out where I missed it. So setting up the equation, we pull out the negative sign, it's here, and then so 0.01 v squared plus 9.81. I think this is okay. Oh, wait. This one should be negative. This acceleration thing should be negative, right? Alright, I think this one here should be negative. It's because if the acceleration is upward, if the acceleration is upward, no, I mean the acceleration is, the velocity is decreasing, so we have a deceleration here. So I think it should be, let's see, even if it's a positive thing, even if it's a positive thing, let's try 0.01 v squared. Times 50 squared minus 9 point, oh no, that's not minus, plus 9.81 to 34.81. I think alright, wait a minute. So let u 2.01 v squared plus 9.81. Okay, du. Alright. I'm lost again. If this is negative, then if this is negative, then the difference that it will make is just it will have a positive value here. Let's try 9.81 divided by 34.81. Sorry, it's not 9.81. This is 98.1. Right, so let's try. This is 98.1. So if this is 98.1, this would be 98.1, and then this one would be 50 squared times 0.01 plus 98.1. Right, so this is 123.1. Alright, so let's try. So this is not it. It should be ln of 98.1 all over 123.1. So let's try to solve this one. Divided by, alright, times negative 500. Alright, so this is it. Okay, so this 113.5 meters. Okay, so actually this makes sense compared to earlier computations that we have. Simply because if you consider the drag, the maximum height should be less than compared to when you don't consider the drag, of course. So here, if you try to, if you notice the maximum for case A is 127.4 meters, and then for case B, we only have 113.5. So I was wrong about this value because I was confused. I'm confusing this one with the value that we have. This is not 9.81. This should be 98.1. So all these should be 98.1 because this is the weight. Alright, so all that just change it to 98.1, and then we're good to go with that. Alright, so that's one of the problem that somehow we encounter setting up the differential equations. So if you encounter a differential equation, I think the first step is to check whether it is a separable equation or not. Okay, so let's just review for the steps that we did. So we have this problem, and then projectile forward upward. So for case A, if we ignore the atmospheric resistance or air resistance, then what would be the maximum height? And then for case B, if we include the resistance, given a 0.01 velocity squared, so what would be the maximum height? So you notice that if there's no air resistance, the equation actually reaches us to the one that we have encountered in the kinematics. And we've solved this value S max is equal to 127.4 meters. Now for case B, we'll include the drag force. So take note, the motion is upward. So the drag force should be the resistance. So the direction is downward together with this weight. So once we have this free body diagram, then we can set up our equations. So in setting up our equations, we have the drag force, so minus the drag force minus the weight, because they're downwards, it's equal to ma. So the acceleration, we should be you should think about it. How will you represent your acceleration? Is it in terms of the velocity with respect to time, or the second derivative of position with respect to time, or this one? So this expression, actually, this is good because you notice we have velocity. We have initial and final conditions for the velocity, and then for the position we have the initial condition. So what's left is the final position. So we can solve this. If we try to integrate or use the separation of variable method of differential equations. Right. So we did a little integral calculus here, and then we just apply the limits. By the way, with regard to the limits, some people actually don't use these limits. They try to produce the integration constant, the C1 and C2 excuse me, so something like that. So it's just the same, actually. Doesn't matter to me or in our class. Wherever you are comfortable, it's okay with me. So if you try to use this the integration constants, then you don't need these limits. So you produce these integration constants, and then you apply the initial conditions, and then you'll be able to solve the value of these constants, and then bring it back again to the general solutions in order to obtain the particular solution. It's just the same. Unlike this one, this is just I think direct. It's a more direct thing, because with limits you don't produce constants like this. So I just put it, integrated it in these mathematical expressions. So that's it, without integration constants. All right, so in the next video, I think we'll do one more problem for the straight line problems, this topic, and then after that, I think we'll move on to no, not tangential. I think path coordinates. Okay, so see you in the next video.